All right. Let's get started. Sorry, we were a few minutes late in the lab today, so that's why we are a few minutes behind. Okay, so Gary was supposed to start today, but we shifted into Friday. So I'll finish the principles of chromatography, and if I have time, I'll start HPLC, but Friday, for sure, Gary will come in for GC and then later MS. Okay, so just to continue, we were talking about resolution last time. What is peak resolution? What's the definition, Pam?
When the are sharp.
Yes, sharp and good separation of peaks. Yes, so resolution means resoluting two compounds from each other, separating them from each other. You get good peak resolution. All right, so what is a solvent front peak? Yes, Zoe?
It's like a small peak you get that shows that the mobile phase has reached the detector.
Exactly. Exactly, that's the key. From the time of injection, when the mobile phase, from time of injection to reaching the detector will say, okay, something just hit me right now. So it shows you a peak. All right, what is the difference between retention volume and retention time? All right, Alexa? Okay, so I would say mostly correct. So the retention time is the time it takes for the compound to actually reach the detector from the time of injection. And then the retention volume is the associated volume of the mobile phase that it took for that compound to reach. And usually you calculate that based on the flow rate. So it's 1 milliliter per minute. And if the retention time is 10 minutes, then it took 10 milliliter of the mobile phase to actually elute that compound. Okay, what is the relationship of peak width to resolution?
So the wider the peak, the poorer the resolution.
Yes, exactly. So when the peak gets wider, that means it's taking longer on the column to equilibrate. So remember you have a number of theoretical plates, which are number of equilibration that the compound goes through as it goes down the column. The longer it takes for equilibration, which is associated with a longer larger height equivalent of a theoretical plate, this will cause the peak to widen because now it's diffusing down the column. So it's going from a sharp to diffused band. So then the peak widens. So as the peak widens, the resolution is reduced. What is the first step in developing a separation between solute of interest in your sample? That means you want to develop separation. What's the first thing you want to do? Michael?
Addressing literature.
Look up literature, find a method, go from it. If there is no method in literature, which you highly doubt that there's always a method, somebody has thought about this before you nowadays. So, but if there isn't, you start with what do I know about the compound? Is the compound polar, non-polar, charged, not charged, small, large? What do I know about it? And then you start with a stationary phase that you think your compound might interact with, and you start with a mobile phase where you keep it isocratic. And then you start looking at ways to enhance separation after that. Okay, we talked about efficiency of the column last time. So I'm going to move along to talk about selectivity of the column. So the selectivity of the column, you might have this image reversed in your slides, but the selectivity of the column is if you have two compounds that are very similar in characteristics. So they are interacting with the column very similarly. So when they're moving down the column, they're not separating very well. So you can change the selectivity by changing either the stationary phase, but sometimes the nature of the mobile phase. I think I gave this example before. Let's say you have that question in your, for the lab report of the HPLC. So if you have a reverse phase chromatography and you're using acetonitrile is a very strong solvent. It's organic strong, it's not polar. So if you're using that and you have compounds like this, two compounds are very close in characteristics, and when you increase the acetonitrile concentration, they're going to come out not separated. If you want to enhance separation, and you know that you're running isocratic at that point, that means your solvent has the same concentration, because if you increase, if it's gradient, they're going to co-elute even more. So the solution is not going from isocratic to gradient. You're already running isocratic here. You're not getting separation. So you say, okay, if I remove acetonitrile and put methanol instead, methanol is still organic. It's less polar than water, but it's more polar than acetonitrile. So what you did test here is you enhance the selectivity between these two compounds. One of them is going to be slightly more polar than the other and will be delayed. And the other one would appreciate a little bit of methanol and come out. Then you get separation. So you enhance the selectivity of your separation by changing the mobile phase completely, the nature of the mobile phase. You can also change the nature of the stationary phase. Obviously, if you're doing strong anion exchange, you can go to an intermediate anion exchange or a weak anion exchange. So you can enhance the selectivity. And the selectivity is designated by the factor alpha, which is the adjusted retention time of peak 2 over the adjusted retention time of peak 1. The higher the alpha, the more separation you have. And good selectivity is more important than efficiency. So separation of two peaks is more important than how narrow the peak is, how sharp the peak is. As long as they're separated, that is more important than making sure that you have a short equilibrium. So, and this is here by this equation. So here it is divided by 4. So the efficiency factor, which is the number of theoretical plate, is over 4, whereas the alpha here has bigger impact on the resolution than the number of theoretical plate, that is the square root divided by 4. So that is just in the equation, it shows you that selectivity is more important than efficiency. The last factor here in resolution is capacity. And I think we talked a little bit about that with the groups that did the HPLC already. So with overuse of the column, two things can happen. One is impurities can make their way to the column and block some functional group. Then they won't be available to interact anymore. So you don't have enough interaction with the column. The other thing, that over time, some of the functional group will be stripped off the column, especially using it, let's say, if it's a reverse phase and using high concentration of acetonitrile and a lot of wash, some of the functional group will be washed off the column. Then when this happens, you don't have enough interactions. So you have your component, let's say A, it used to come out at 15 minutes, started coming out at 13, 12, 10 minutes. So it just shortened the retention time because there's not enough capacity anymore on the column. So this would cause A not to separate from another compound that used to come out around 8 minutes. So now they're both coming out sooner and having less interaction with the column, so you lose the separation. So over time, capacity of your column will be impacted. You can prevent that by using guard columns. In the HPLC, there is a guard column that you would use. We'll talk about it in the HPLC lecture, and those of you that took the HPLC lab already heard about it. In the GC lab, you cut the column. So you have your capillary column, and the top of the column that has impurities, you cut it off. So you prevent impurities from going down your column. In the HPLC, to prevent impurity, you put the guard column that captures the impurity. So you kind of preserve the capacity of the column for as long as you can, and also maintaining it, not overusing it excessively with strong solvents so that you don't lose functional groups. But at some point, capacity will be impacted. Okay. So there are two types of analyses with chromatography. There is qualitative analysis and quantitative analysis. With qualitative analysis, we're often looking at identification, detection and identification, not necessarily determining amount. And in the GC lab, you do something called semi-quantitative. So you did the identification, the detection, the identification, and you calculated the relative area, which will be not quantitative because you didn't do standard curves. So there is qualitative, there's semi-quantitative, and there's quantitative. With qualitative, you're not doing any form of quantitation. So you look at, I want to identify my peaks. I want to detect presence of certain compounds. In order to do identity, is you compare, one thing you do is you compare retention time with standards. We did that in HPLC, we did that in GC. So you run standards, you look at the standard and see how long that standard took to leave the column, and you say, okay, this is my compound because it has similar retention time. But sometimes it's complicated. Sometimes you have very close retention times of the compounds. They are not separating. They are barely separating. But in order to identify them, sometimes you have very nice sharp peaks, but they're two of them. And they're very close, like a few seconds apart. And you go, I don't know. I ran the standard alone. It's giving me somewhere here. I don't know which is which though. This is my standard. This is my sample. This is my standard. I don't know which is which. In this situation, what you would do is you spike your sample. So you take the standard and you put the standard with your sample. And you run again, and then you will see something like this. So this increased. So this means this is your compound that you're looking for, because it increased in peak area after you added the standard to the sample. Photodiode array detector, we talked about it in HPLC lab. Those of you that took GC did not hear about it yet, but it's a type of UV detector or UV vis detector. So that measures absorption over a range of wavelengths. So you get, we'll talk about it in more detail later, but you kind of get something like we call spectra. So in a chromatogram, you see time versus absorption. That's the chromatogram. But with photodiode array detector, you see another window here. that gives you absorption over lambda or wavelength. Every split of a second, you get an absorption reading at different wavelength. So let's say it's 300, 305, 320, etc. Obviously 300, 301, 302, you get. And if you're measuring absorption over UV, so it will be 200 to 400 nanometer. So you get absorption at every wavelength. This gives you a fingerprint of the compound. Every compound that absorb light that have different structure, they will have a different shape of absorption over lambda, shape or spectra. So this allows detection based on the characteristic of the compound. So this is good, a strong UV detector. We'll talk more about its principle later. Detection using multiple detectors. So sometimes you have compounds you're trying to separate compounds that absorb light and compounds that don't absorb light. So sometimes you use a UV detector combined with light scattering, for example, or refractive index detector. So we'll talk about different detectors that allow differentiation between compounds that have different characteristics. Sometimes you have a compound that has the same lambda max. So what is lambda max? Those of you that took the HPLC lab, what is lambda max? What's lambda max? Abi?
To get the maximum.
Maximum absorption. So it's the wavelength at which we get maximum absorption. Okay, so two compounds might have the same lambda max. Let's say this compound here, 259, and then this compound, okay, 359, oh, 320, just to make it look like that, 320. This compound have lambda max at 320. This compound has lambda max at 320. But this compound absorbs light at 280, let's say. This one does not absorb at 280, 0, or whatever, very low absorption. So what you can do, you can measure at 320, and you can measure at 280 and take the ratio. The ratio is different, then you have different compounds. Sometimes you use separation using another chromatography. So if you have compounds that have similar molecular weights, if you're using size exclusion, they're not going to be separated. So you use size exclusion, then ion exchange, then they get separated based on charge. Then you can separate them and identify them. Mass spectrometry is a whole different world where it's a very powerful tool. You can, even if you don't get good separation, you can get different mass spec data, mass over Z or molecular weight over charge, and you can identify compounds even if you don't have resolution, which Gary will talk about in the MS lecture. Okay. Quantitative analysis. So here, in order to quantitate, you would need to have standard curves. So in order to quantitate, we need to determine area under the curve, which is very important to relate area under the curve to concentration. So if you have, again, I'm going to plot here time And here it could be absorption, it could be fluorescence, it could be from FID detector, ionization, conductivity, it could be anything. But this is always going to give you a peak. The area under the peak is what we care for to plot against concentration, known concentration. Okay, so it used to be, sometimes you say, should I take the height and relate it to concentration? Or should I take the area and relate it to concentration? So this is the height. Should I take the height only, or should I take the area? We go with the height. No, sorry, we go with the area. So why do we go with the area? Because the height changes with, with time. When you run the sample and the column characteristic change, the height will change, but the area might stay the same. So instead of being sharp, your peak might widen a little bit. So it might get shorter, but the area here might be the same as the area above. It's just got shorter and wider. So that's why the width is important. So we need to take the height and width into consideration, therefore the peak area. So now we can have software that calculates the area for us. In the past, there would be a strip chart recorder. You would take the print out, you cut the peak out, and you weigh it. So that's how you would relate the concentration to the area under the curve. So, but now we have softwares that gives us the area, and that's what we use for quantification. So, two important things I want to talk about, and it relates to a question you have in one of the lab reports. I don't remember now which one. But what you have here, external versus internal standards. One thing you need to get straight. Without an external standard, you cannot quantitate. You need to have an external standard. So what is external and what is internal? External meaning a standard you prepare outside of your sample, not with your sample. So you prepare standards alone and you run them alone of each of your compounds of interest. So that's what external is. Internal, it means you add a standard, reference a standard to your sample. So that's internal versus external, whether with the sample or not with the sample. So, but okay, so each of them have different functions. Okay, so what we need to do is understand the function of each. What you did, those of you that did the HPLC lab, did an external standard where we got caffeine and we prepared different concentrations of caffeine, ran them on the instrument, got area under the curve, and we plotted a standard curve here. So you got the area and you prepared different concentrations, and then you plotted the concentration, the area, and you got standard curve with the equation of the line, which you will use to predict the concentration of caffeine in different samples. Okay, this is very simple. External standard, and then you get your concentration. Internal standard is important too. We don't use it in simple sample preparation techniques, like you did for the HPLC. It was just different beverages, dilutions. There are not a lot of steps. Take the GC lab, where we have different fatty acids. We want to determine fatty acid composition. There's a lot of steps. So first of all, you saponify the fat. So meaning you break down the triglycerides into fatty acids. And then you react the fatty acids with methanol. So you get methyl groups attached to the fatty acids. There's a lot of steps, a lot of reagents that you add, salt, hexane, a lot of reagents. You'll see that in the lab if you haven't done that. So at every step, there is a chance of loss. There is a chance of error. So when you take these fatty acids and you run external standards, oleic acid, linolenic, linoleic, steric, all of these fatty acids, you prepare external standards like you did, great, you can quantitate. But if you have losses during sample preparation, you're not able to account for these losses. If you use an internal standard, so the internal standard correct for losses during sample prep. So how does that work? So you have to select an internal standard that is different from your fatty acids that you're trying to calculate their concentration. So if you're looking at oleic, steric, linoleic, linolenic, whatever, you do not want to use any of these fatty acids as their internal standards, because that will increase the concentration. You would choose, like say, a C4 instead of C18, C20, C22, or C14, those are your different fatty acids. You choose a C4 fatty acid that is not present in your sample. So it has similar characteristics to the fatty acids. And so it will elute or come out in the same time frame of your analysis under the same conditions, but it will not co-elute with any of your fatty acids of interest. So the characteristics of your standard, internal standard, should be similar in structure. These are the three important characteristics I'm going to mention them now. Have similar characteristics to your actual compound, but different so that it does not come in co-elute. So it doesn't come at the same time. And it comes out during the entire analysis time. So if we look at this here, this is in molasses. Sugars in molasses are glucose, fructose, and sucrose. You don't have lactose in molasses. Lactose is present in dairy. So, but it is a disaccharide. So it has similar characteristics. So I add lactose to my molasses as an internal standard. It's coming out here, this third peak, in the same runtime, the 10 minutes of my analysis time, and it's not co-eluting or interfering with any of my glucose, fructose, or sucrose. So, three things. I'm going to repeat that. Similar in structure, disaccharide here in this case, similar to sucrose, does not interfere with any of my peaks, any of my compounds. Second characteristic. Third, it comes out within my analysis time, not later, not like 30 minutes later, within the 10 minutes of my analysis. So these are the three main characteristics of my internal standards. What does it do? So when you add it at the very, very beginning of your sample prep, you took your molasses or you took your oil sample, whatever it is, you add directly your standard to it, and then you start your sample preparation. So any losses that will be inflicted on your components will also be inflicted on your internal standards. Okay, then how does that help me? When I want to plot my standard curve, so this is, I have three compounds, X for one compound, Y another, Z another. So I'm plotting the standard curve for each compound, so I need external standards. Internal standard alone doesn't work to calculate concentration. So you still need your external standard. You still need your glucose, fructose, and plot externally your standard. But the difference here, you prepare your standards. Let's say I'm just going to say glucose. I add to it lactose. Okay. Or if I'm doing C18, oleic acid, C18 with the one double bond. So C18 oleic acid, I add C4. Okay. In my standard. And also in my sample, I add my internal standard, whatever it is. So I add it to my standard, I add it to my sample. So now I have internal standards in both. And then I run them separately. I run my samples, I run my standards. And then what I get is when I plot, I have my concentration of my standards, glucose concentration, 1, and then I have 2, 3, 4 different concentration, all have the same concentration of lactose. All will be added the same concentration and the same concentration here. One specific concentration I select for my internal standard, but I add to all my concentrations of my standards and to my sample. All right, then I can plot here the concentration of the external standard. And here I plot the area under the curve of my standard to the area under the curve of my internal standard. So I'm correcting for the internal standard. So here is a ratio, area of the standard over the area of the internal standard. And then I get the equation of the line. Now for my sample, I take the area of glucose, this one, in my sample. I divide it by the area of lactose, also in my sample, and then use that as the y to determine x in my unknown sample. Okay. You want me
And the concentration, is that of the internal standard? Could you go over that again?
Okay, the concentration of the internal standard will be fixed. So you would pick a concentration that would be within your range of concentrations that will show up on your chromatogram, not too concentrated, not too dilute. So you choose one concentration and you say you put the same concentration in all of your external standards and the same concentration in all of your samples. Your external standard, you prepare a different concentration, like we did with the caffeine. We prepared, I think, I don't remember, what was the concentration we had? 100 ppm, 150 ppm, and 200 ppm, is that it? So you prepare your different concentration of standard, but to each of them, you add the same amount of your internal standard. Okay? Yeah. Was that your question?
And then just for that graph, can you explain the y-axis and the x-axis?
Yeah, so here the concentration, because you vary the concentration of your external standard. So here is the concentration of your external standard. And here is the absorption of the standard, the external standard, to the concentration of the internal standard, not concentration, sorry, area. Area of your standard, external standard, over the area of your internal standard. And you get that, you get your equation of the line, and then this is your sample. You want to determine how much glucose you have in your sample. You take the area of peak 1, you divide it by the area of peak 3, your internal standard. That will be your y. You put it in the equation of the line, you get the x, which is the concentration of glucose.
Can you use an external standard without using an internal standard?
Yes, you can use an external standard like we did in the caffeine lab. We only did caffeine standard external. We didn't have any internal standard that we added to the sample. So you can do that. But if you want to account for any losses during sample preparation, especially for the GC lab, it would be good to have an internal standard so your quantification is more accurate because you account for losses in the internal standard as well. So losses of sample, losses of internal standard.
Could I, for example, add my so like I have my standard annual concentration of it, I add to my sample, I compare it, and then I will know how much I lost and I have a percentage of loss. Would I do that instead of having my internal standard?
How would you won't be able to determine the percentage of loss without converting it to a concentration? Like a factor? The factor of loss?
Because I would know how much I added before and how much I added at the end. So there I would kind of skip one step.
I'm not sure I'm getting exactly what you're saying, but we can talk about it later.
So then, just so there's no reason that we have to just use an internal standard solely by itself.
We use it by without quantification. There's no, if you're not after quantification, it's really no need to use an internal standard.
Okay, but I'm saying like we would never use an internal standard without an external. It just
Without quantification, sometimes you use an internal standards just to check that your preparation of your sample is accurate and you're not losing your compounds during preparation. So you have your internal standard as a check that, okay, the sample prep is going to preserve the integrity of my components. So you have your internal standard, you know how much you added, to see if it's still there or not. But usually, quantification, you find out your external standards for sure, and then the internal standard helps with correcting for areas of loss.
would be our internal standard.
No, exams were so.
Then what was our internal?
We didn't do them. We didn't. We didn't do quantification. We didn't correct for any losses during sample. So we didn't do quantification that is full quantification. We did semi. What you did is you determined the area under the curve and linked to composition. This is not full quantification.
Yeah, but if we were to, we would have like maybe something C4.
C4, you would add it to your oil.
Yeah.
And then you would do the whole sample prep. And then you would have external standard. For every fatty acid, you would have the standard for it and run the standard for it, which you didn't do.
Will there be any reason behind like doing it and
No, the lactose here is not part of you won't find it in molasses. So you don't really want to quantitate it in the molasses. It's not there. So you don't use it as an external standard for this. It's an internal standard. It might be an external for lactose in milk. Yeah. Any more questions? What's that? The y-axis is the area under the curve, the area of the peak under the curve. But when you have an internal standard, you correct it by the area of the internal standard. So you have your internal standards prepared with your external standards. So in the solution of your glucose, you add lactose, right? And then you run it. Then you would have, in your standard, you will have glucose and lactose. You take the area of this or the area of that, and then you plot it.
this is not the
This is standard curve. This is a standard curve for, let's say, glucose, fructose, and sucrose. So here's 3 standard curves. You don't have to plot 3 standard curves on one. I'm just showing you. It would be 3 separate ones.
That means I'm using the area ratio.
Yeah, ratio. Yeah,
That's
it's a
how
ratio.
something.
Yeah, it's the ratio of the area of the actual standard over the area of the internal standard. It's a ratio.
The actual one is not shown. in this graph.
What?
The actual one is not shown. in this one for the standard. The standard line.
Yeah, it's the calibration first.
Yeah, and this is the specific picture. The actual graph is not shown. We are standardizing, right?
It's the calibration curve.
Yeah, that's why the actual line is not shown. Yeah.
What
Can
actual
I get the
line?
actual line, like my sample?
Your sample doesn't have a line. Your sample has an area. Here, you take the area and it will have the area of your internal standard, and this is your compound. So you take the area of this over the area of the standard, that's your Y, is the area over internal standard. That's your Y. You have your equation of the line that Y equal AX plus B. That's your Y. And you calculate for X. Right? This is standard curve. Oh boy, good. What? I was hoping to start HPLC, but what do you think? All right, yes.
We're like solving it for someone instead of solving for Y or solving for X.
You never solve for Y.
Well, let me just say that your Y is your area of your sample divided by the area. And
Yeah, so
So
you
you
add
would
the concentration, right?
Huh?
You're trying to find the concentration in your sample. What do you use? You run the chromatogram, you get area.
yeah, no, you're it's like we're solving it backwards in terms of like normally we would solve for Y and get all of our
Normally when?
Like a normal algebra.
Yeah, so I think what he's saying is, in this scenario, we, from the
You always
chromatograph,
solve for
we get
X.
Y in the scenario.
In the scenario of food analysis.
Yeah.
In the scenario of food analysis, you're always solving for the concentration.
Yeah,
And the
which is-
concentration is always the independent factor, and your dependent factor is Y. Yeah.
Yeah.
Oh, yes, that's a great question. Yes, you have a question? Yeah. No. I thought I had. All right.
There's too many standards.
Too many standards?
Too many standards.
There no? I know it's confusing, I know, but listen to the lecture again if you want to mold it over in your head, and come see me during my office hours, happy to re-explain any concept. I'm gonna stop here, give you a break, and I'll see you on Friday.
Thank you.
Oh, yeah.
I just want to put this out.